Hello everyone, welcome to the ISARC2016 Technical Workshop. This is a demo of the automated laser scan planning algorithm. I am the main author of this algorithm, Cheng Zhang, from Arizona State University. This laser scan planning algorithm can help the users of the 3D laser scanners to select optimal scanning positions and parameters in order to collect 3D point clouds with required data density within minimum data collection time. In this demo, I will show you how to use this algorithm and the data collection result following the plan generated by this algorithm. In order to test this algorithm, we prepare 3 buildings with different size and shape as the laser scan planning target. You can find these buildings on Google Earth according to the coordinates of each building. In this demo, we will use the first building because it has the most complicated shape and the largest size. The input of this algorithm is the list of point goals generated according to the 3D as designed model. These point goals include the corners of windows, points along the edge of walls, and the corners of walls. In addition, we set the level of detail requirement of each point goal as 25 millimeters, which is 1 inch. This means in the collected point cloud, the distance between adjacent points should be less than 1 inch at the neighborhood of each point goal. This generated point goal list is saved in the file fpinfo.mc, which can be found in the algorithm folder. Open this point list. We can see the point goal list consists of 8 columns. Column 1 to 3 are the XYZ coordinates of each point goal. Column 4 to 6 are the normal vector of the surface where the point goal locates. Column 7 and 8 are the horizontal and vertical level of detail requirements in millimeter. Now let's open the MATLAB code file fmain run this in the MATLAB editor. And then click Run. In the command window, the algorithm will ask you to pick one building to generate a scan plan. Let's input 1 to select the first building, which is the McCord Hall in Arizona State University. Then the algorithm will show you all the point goals of this building. You can rotate the figure to view the point goals in 3D. Press any key to process the divide function, which is clustering the point goals according to the visibility contradiction relationship. After several minutes waiting, this figure will show you the result of features of a point goal clustering process. You can see that all point goals will be divided into clusters according to the visibility contradiction relationship, which means different point goal on different side of a building will be divided into different clusters, and adjacent point goals will be divided into the same cluster. After pressing any key, we are moving on to the next function, which is the conquer function. Identify the scanning position and resolution for each group. In here, we identify the scanning position for the orange group on the corner. Let's have a look. You can see for this group of point goals, the algorithm generates the feasible scanning position is shown in this colored block. The color is purple. Keep pressing any key, we can generate the scanning position for each group, and the corresponding resolution is shown in the command window. Here, the algorithm finished generating the scanning position and resolution for all clusters of point goals. And the red cross here shown the remaining point goals which are not be scanned in previous step. In the next step, we're going to process the garbage collection function, which is identifying the point goals for these remaining point goals to complete the scan plan. Some of you might ask why these point goals, which is very close to the scanning position, are not scanned in the previous round. You can make a guess here. Let's press the key and continue the program. In the final step, the algorithm generated this scanning position for the remaining point goals in the previous step. Some other point goals either are scanned by the scanning position in other groups, such as these garbage scanning point goals. Some other point goals are discarded for higher efficiency. For example, this. This is the final step of the scan planning algorithm. In the real-world laser scan projects, we may want to modify the scan plan based on the real-world environment in order to minimize the occlusion by the vegetation and other objects. Then we can use a 3D laser scanner to scan this building according to the generated laser scan plan. And this is the collected point cloud after registration. If we keep zooming to see the detail of the point cloud, we will find that for the neighborhood of each point goal, the distance between adjacent points are within 1 inch, which is 25 millimeters. Because this data is too big, so let's cut one piece of the data to show you the process of zoom in. Now I'm zooming this data. You can see this is the neighborhood of a point goal, and this length is 1 inch, which is 0.025 meter. And you can see that the distance between adjacent points are just below 1 inch. You can do this to any point goals of this building. Also, you can try to use this algorithm to generate the scan plan for the other two buildings. Thank you for watching.